Hello there. After learning the ropes in indie arrays and what data they are compatible with, it's time to move on to NumPy's functions and why we use them. In the next two lectures, we'll examine several features and parameters that most NumPy functions support. We'll refer to these parameters as universal because they are closely tied to the universal functions. That being said, let's begin with some definitions. Universal functions are a special type of functions which work with indie arrays on an element-by-element basis. Therefore, you can think of universal functions as an extension of the element-wise operations we examined a few minutes ago. These include some mathematical operations, as well as trigonometric and comparison functions. Apart from that, they support several useful features like broadcasting, typecasting, and computing over a given axis. To best understand these concepts, we'll need to look at a few examples. So let's jump into Python and set up some indie arrays. We're also leaving a link to the documentation page for universal functions in case you want to read up on them on your own, or check out what type of functions are classified as universal. For a sneak peek, click on the link now. Okay, back to Python. We'll continue by defining three variables of different sizes, arrays A and B, as well as matrix C. The first two will be vectors, while the last one, as the name suggests, will be a matrix with numeric values. If you're coding along, feel free to pause the video now and set these variables up. All right, now that we have our example variables ready, we can move on to broadcasting. So, what is broadcasting and how do we use it? Sometimes we want to conduct element-wise operations but have variables of different sizes and/or dimensions. In those cases, we can broadcast the smaller variable and create a broadcast version with the size of the larger one. You can think about it as stretching one variable over the other to produce an output with the same shape as the larger one. To get a better sense of how this works, let's use NumPy's universal function add and add up array A and matrix C. Even though the former is a vector and the latter a matrix, the function compiles because their sizes are broadcastable. We will shed more light on the meaning of this term in a minute. The output we obtained is a 2x3 matrix where we've added array A to each row of matrix C. So, we broadcast the array onto a 2x3 matrix, which has the same values in every row. Then, after having two matrices with the same shape, we conduct element-wise addition between this artificially created matrix and matrix C. Similarly, if we use array B instead of array A, we are broadcasting a column into a 2x3 matrix, where every column holds the values in array B. Then, we're adding that up with matrix C to get the output we see on screen. Superb! If you're new to indie arrays, broadcasting can seem extremely complicated at first, because you really need to know what you're doing to avoid making mistakes. That said, once you realize we're just matching arrays of different shapes in order to use a given function, the process becomes much more digestible. A minute ago, we mentioned that the function compiles if the sizes of the two variables are broadcastable. Remember? That is because there are certain rules to broadcasting, and we can't just broadcast any variable to a new shape as we did with arrays A and B. These rules are three and are as follows. The arrays have the same shape. The arrays have the same number of dimensions, and the length of each dimension is either common or 1. The arrays that have too few dimensions can have their shapes altered with the dimension 1 to satisfy the second rule. In both examples we showed, we followed Rule 3, where we stretched the 1D vector into a matrix, which led to us having the same shape as matrix C. For a more in-depth explanation of these rules, along with some examples, you can check out the documentation link we provided above. Great job! Now that you've grasped the concept of broadcasting, we're ready to explore more characteristics of NumPy functions. Next time, we'll continue with typecasting and calling a function over a given axis. Thanks for watching.